Hola, hi, this is Al, your statistics instructor. Let's get to work. The plan for this video is the following. Number one, we're going to be talking about the 68, 95, 99.7 rule. This rule approximates the proportion of observations contained in 3 different intervals for normal distributions. Number 2, we will also talk about the 1.5 Iqr Rule, which will help us identify potential outliers. Goal number 3 for this video. We will carry out a simulation to see what is the typical aspect of a histogram, box plot, and QQ plot for a sample of observations that are normally distributed. Number 4. Finally, we assess the normality assumption for a dataset. Let's begin. Okay, so we said point number 1. We are going to talk about the 68, 95, 99.7 rule. Okay, so what this rule states is that if you have a normal with mean mu, right, a Greek m, and standard deviation sigma, a Greek s, right, so between mu minus sigma and mu plus sigma, you will have roughly 68% of the observations. Okay. On the other hand, if you pay attention to the following interval, mu minus 2 times sigma and mu plus 2 times sigma, you will have roughly 95% of the observations. And the last part of the rule is that between mu minus 3 times sigma and mu plus 3 times sigma, you will have roughly all the observations, 99.7% of the observations. Okay? Okay. So, we can check, right? Let's launch R. Again, remember that these are just approximations. Okay, so we know that if we want to find, if we want to evaluate the CDF at the point, okay, of normal distribution, we can use the following R command. P norm is a function that is going to help you evaluate the CDF, meaning it's going to give you the area to the left of a particular point, right underneath the probability density curve of a normal. So, for instance, the first part, right, we said that between mu minus sigma and mu plus sigma, we should have roughly, right, we could write it down like this, probability that a normal 0, 1 is between those guys, mu minus sigma and mu plus sigma is going to be roughly 68%. Okay, and remember that I'm using that hashtag because it's just a comment, right? R will ignore this. Okay, so now here comes the command that I'm going to be using to compute the proportion of observations between mu minus sigma and mu plus sigma. So note that by default P norm is going to be assuming that you are interested in a standard normal, meaning a normal with mean 0 and standard deviation 1. Okay, so let me be, in this case, very specific, right? Mean 0 and standard deviation 1. Okay, so that would give me the area to the left of 1. Okay, and then I'm going to subtract the area to the left of -1, and that is going to give me the proportion of observations that I want, right? Between 1 and -1. Okay, so yeah, it seems that the rule works. Okay, now note that you could just do it like this, right? Since the default is a standard normal, you could find that proportion that you are interested in just like this. Let's test the second part of the 68, 95, 99.7 rule. Then in that case, two standard deviations for a standard normal is just between -2 and 2, so that works. And last part of the 68, 99.7 rule, this, right? So roughly 99.7% of the observations. Remember, it's just an approximation, so but it is a good approximation. Okay, so now we are done with the 68, 95, 99.7 rule. Okay, let's talk about the second point, the second objective of this video, the 1.5 Iqr rule. Okay, so let me go back to our lecture notes here, and as we mentioned at the beginning of our video, this rule is going to help us identify potential outliers. Okay, so the idea is the following. We are going to compute two numbers. Okay, we're going to compute, let me write it down here. We're going to compute the something called the upper fence, which is going to be Q3 plus 1.5 Iqr, and the lower fence is going to be Q1 minus 1.5 Iqr. Okay, and it turns out that if you have a number that lies to the left of Q1 minus 1.5 Iqr, the interquartile range, okay, meaning the difference between Q3 and Q1, then that observation is a suspected outlier. On the other hand, the second part of the rule is that if you have an observation that lies to the right of the following number, Q3 plus 1.5 Iqr, which is referred to as the upper fence. Anyway, if you have a number that lies to the right of the upper fence, then that guy is also a suspected outlier. Okay, so let me just write that down. So 1.5 Iqr rule. Again, we're going to have something called the upper fence, which is just Q3, the third quartile, plus 1.5 Iqr. And again, remember that Iqr just stands for the interquartile range, so it is just the difference between Q3 and Q1. Okay? Lower fence, it's going to be defined similarly, but instead of a plus 1.5 Iqr, we are going to have a negative 1.5 and instead of Q3 we will have Q1 here. Okay, make sense? Okay, so if, right, if x, a number, is greater than the upper fence, then x is a suspected outlier. Or if x, generic observation, is less than the lower fence, then x is also a suspected outlier. Make sense? Okay, now let me show you something. Let's find Q3 first. Okay, so Q3, it's the third quartile, which is just going to be, you know, a number such that it has 75% of the observations to its left, right? So we know that the default is the mean is 0 and the standard deviation is 1, but let me be very specific here. Okay, so Q3 for a standard normal is just 0.674 roughly. Okay, now let's find Q1, the first quartile. So the first quartile of a normal distribution is a number such that you have 25% of the observations to its left. Okay, so Q1, guess what, happens to be the negative version of Q3, right? Okay, so let's just do a little bit of algebra here, right? So note that the upper fence, let's just say this, note that Q1 equals negative Q3, right? We just saw that for a normal, right? Okay, so we could rewrite the upper fence like this. This we know is just Q3 minus Q1. But then what we have here is Q3 plus 1.5 Q3 minus Q3, right? Because we know that Q1 is minus Q3, right? So we end up with Q3 here, right? So we have Q3 plus 1.5 2 times Q3, that's just Q3 plus 3 times Q3. So this is just 4 times Q3. That would be the upper fence. Okay? Doing similar calculations, since Q1 is the same as minus Q3, and then we would have negative 1.5 times Iqr. We know that we would have minus, in the end, right, we are going to have minus Q3. Here, minus Q3 minus 3 times Q3. So in the end, what we have here for the lower fence is just minus 4 times Q3. Make sense? So let's find what's the proportion of observations between the upper fence and the lower fence. Okay, so let me create an object called upper fence, which is going to be just we know from what we did that the upper fence Q3 plus 1.5 Iqr, right, is the same as 4 times Q3. 4 times Q3. Okay, so the upper fence looks like this, right? And again, from the algebra that we did, we know that the lower fence is just negative 4 times Q3. So lower fence minus 4 times Q3. Okay, so what we want is the proportion of observations between the upper fence and the lower fence. Okay, so to do that we use something like this, right? So it would be P norm of upper fence minus P norm of lower fence. Again, that is going to give us the proportion of observations between the upper fence and the lower fence, meaning Q3 plus 1.5 Iqr and Q1 minus 1.5 Iqr. So 99.3, right? So what we're saying here is that for a normal 0, 1, right? So only 7 out of 1,000 observations are going to be either beyond the upper fence or below the lower fence. Make sense? So those are extreme observations, right? Well, we should take a second look at them, right? Because they are extreme, they are rare. Let's test drive the 1.5 Iqr rule. Okay, so what we're going to be doing next is a simulation. We're going to generate a sample of 1,000 numbers coming from normal 0, 1 and see how this rule works in practice. Okay, so first let me show you something. If you use the following command, set seed, when you generate a sample, you're going to get the same numbers, okay? And you may want to use this for to make your results reproducible, right? So you end up with the same random sample, right? If you don't care about reproducibility, then you don't have to do this, okay? So just let me show you something. If you do this and you generate just one random number from a normal, right? There you are. So if I use this set seed, when I generate another random number, I get the same one, right? So this is in case you know, you need to be able to reproduce your results. Okay. If you don't need that, then forget about this guy and then just you know, generate it like that, and then you're going to get a different one every time. Okay, anyway, in this case, let me do this, right? Just so you see how it works. So the sample that we're going to generate, it's a sample of 1000 numbers coming from a normal 0, 1. Okay, and what I would like to do is test drive that rule that we talked about. Okay, so now for this guy, right, for this sample, I would like to count the number of observations that are below, well, that are between the upper fence and the lower fence. Okay, so to do this, we're going to do the following. We're going to be subsetting our sample. This guy here, let me show you, just is a vector with 1000 numbers. So what we want is we want to identify which of these guys satisfy this, that they are below the upper fence, upper fence, and above the lower fence. According to the theory, since we generated 1000, so roughly 993 out of them, right, should be there. So those are the guys that satisfy that, right? So now with the following command, length, I'm going to count how many I have. 992. Okay, so it makes sense, right? It's very close to what the theory is telling us. Make sense? Yeah, because remember what we had here in theory. Right? So really close. Okay, let's continue. So number 3, what we said is that we wanted to carry out a simulation, right, to see what's a typical aspect of a histogram, a box plot, and a QQ plot. Okay, so as far as a histogram goes, and we know that we can do something fancier than what I am about to do, right? We're going to be using just base R, but you know now how to use ggplot2 to create nice histograms, or even base R and make it look nice. But here I just care about the results and the general behavior of sample coming from normal. Okay, so I'm going to be making very basic graphs here. So using the same sample that we just generated to test drive the 1.5 Iqr rule, I'm going to make a histogram of that sample. So no surprises here, right? We know what the PDF of a normal distribution looks like, and this histogram is an approximation of such a PDF, right? It looks roughly symmetric. We have a single peak, and yeah, given that now we know the empirical rule, most of the observations lie between -3 and 3, as we should expect, right? So no surprises there. Now let's make a box plot for that sample. And these guys here, right, these hollow circles, right, these guys are the points, the 7 points that lie outside the fences, right? Well, it would be in our case for our sample, 8 of them are outside the fences. This guy here, this horizontal line, represents the upper fence, meaning Q3 plus 1.5 IQR. This guy here, this horizontal line here, is the lower fence, meaning Q1 minus 1.5 IQR. And these guys here are identified by the 1.5 IQR rule as potential outliers. Make sense? And we have 8 of them. But we know that that is normal. Actually, these guys come from a normal distribution, and even for normal distributions, that's something expected. We expected something close to 7 of those guys outside the fences. And for this particular sample, we have 8 of them. So, okay. They behave as they should for a typical normal. And finally, let's make a QQ plot for our sample. So we know that to create a QQ plot, just use that R command, QQ norm. Okay. And then we know that the closer are those points to form a perfect straight line, the more reasonable the assumption of normality is. In this case, this sample comes from a normal, from a standard normal. So yeah, it looks, you know, these points look very close to forming a perfect line. We could add that line, the theoretical one, with the command QQ line. Let me make that line red. There we are. Okay, makes sense? Okay, so goal number 4. We said that we would like to carry out a simulation to see what's the typical aspect of normal, but also we wanted to do that to compare that behavior with the one for a different data set. Okay, so that was the last goal of this video. So maybe you remember that we dealt with this data set, Faithful, right? It's part of the data sets included in R. So let me just remind you that if you type data and then you open and close brackets, then you can see the data sets contained in base R. The one that I want is Faithful, right? So there you are. Okay. So let me just remember what are the names of the variables contained in that data set. So eruptions and weighting. Okay. So what we're going to be doing here is well, comparing what's the behavior of say eruptions, right, against the typical behavior of normal, right? A sample coming from a normal. Okay, so here we go. Let me use the command attach, so I can use the name of those variables. So first, let's make a histogram of eruptions. Clearly, that doesn't look like the histogram for a normal, right? Doesn't seem to be symmetric. It has more than one peak. So if we were to assume initially that eruptions had a normal distribution, now after seeing the histogram we go, that assumption wouldn't be reasonable, right? We could make a box plot. And oh, well, we know that it should look roughly symmetric, and clearly it is not symmetric, right? It seems to be skewed. So again, more evidence against the assumption that this variable eruptions is well approximated by a normal distribution. We could make a QQ plot, and then these guys are very far from forming a straight line, right? And that's what you would expect. That's a kind of pattern that you would expect for a QQ plot if the observations come from a normal. Okay, so we could add that line yeah, so it's really far, right? And maybe something else that we would like to do is something like seeing if we know that for all normals the 68, 95, 99.7 rule should hold, right, approximately. So what we could do is find the mean of eruptions, the standard deviation of eruptions, a lower limit. We know that the first part, the 68% part of the rule, is that between the mean minus one standard deviation and the mean plus 1 times the standard deviation, which we should have roughly 68% of our observations, right? So let's count for eruptions, right? First, let's see how many observations we have there. Okay, let me call that guy n. That 272, that's a total. Now let's count how many of those observations lie between lower, right? So eruptions have to be below upper and above lower, right? These guys. But I need to know how many of them satisfy that. So now, if we want to know the percentage, we just divide by that 272, right? So roughly 55%. So really far from the 68 that you would expect for a normal. So anyway, after examining the histogram, the box plot, the QQ plot, and checking, for instance, the first part of the 68, 95, 99.7 rule, well, we conclude that for that variable, eruptions, the assumption of normality wouldn't be that reasonable. Okay? Okay, so let's summarize. So what we did today is we talked about the 68, 95, and 99.7 rule. Okay? So what that rule states is going to give you an approximation of the proportions that you would expect for 3 different intervals. So for instance, if you're between if the interval is mu minus 1 times the standard deviation and mu plus 1 times the standard deviation, you would expect for a normal to have 68%. Okay? We also talked about the 1.5 Iqr rule, right? And what that rule is going to help you do is identify potential outliers. Okay? And then what we did in this video was carrying out a simulation to see what was the typical behavior, what you would expect to see as far as graphical summaries go for a sample of observations coming from a normal. We did that for a histogram, for a box plot, and for a QQ plot. And finally, what we did is we used those tools to assess the normality of a sample of a data set, in this case eruptions. Okay, and in this case, using these tools, the assumption that that variable eruptions has a normal distribution doesn't seem to be reasonable. Okay, make sense? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.